Hello friends, this is the fifth part of name reactions. In this part, we will see Wittig reaction. Aldehyde or ketone on treatment with phosphorus elite gives olefin or alkene. This reaction is known as Wittig reaction. So here, one example cyclohexanone. This cyclohexanone on treatment with methyl triphenyl phosphorane. Methylene triphenyl phosphorane gives methylene cyclohexane along with triphenyl phosphine oxide. The preparation of phosphorus elite. This structure is known as phosphorus elite, in which there are plus and minus or positive and negative charges are adjacent to each other. This negative charge is on this carbon. So the preparation of phosphorus elide, or it is also known as Wittig reagent, involves following steps. Triphenyl phosphine reacts with methyl bromide to give phosphorus phosphonium salt, methyl triphenyl phosphonium bromide. And this reaction is carried in organic solvents such as benzene. This phosphonium salt, in phosphonium salt, this alpha CH. So this is alpha carbon, and this carbon hydrogen bond is very weak, or it is acidic. The weakly bonded hydrogens are known as acidic hydrogens. In this phosphonium salt, this alpha carbon hydrogen bond is weak or it is acidic. On treatment with strong base such as N-butyl lithium or phenyl lithium, loses this alpha hydrogen and it forms a light. And this negative charge comes here. After removal of this hydrogen. And this phosphorus, in this phosphorus elite or Wittig reagent, the negative charge and positive charge are adjacent to each other. This phosphorus elite is resonance stabilized. That is, this negative charge can form double bond here. We can get this doubly bonded compound, and reversely it can form negative charge on the carbon and positive charge on the phosphorus. So it is resonance stabilized phosphorus elite. So it is a stable one. The mechanism of the Wittig reaction, it involves the steps. In step one, what happened? Nucleophilic attack of the this negative charge of the elite on the carbonyl carbon of the carbonyl compound, and this carbon carbon double bond will convert into single bond and here negative charge. This compound is known as betaine intermediate. And this betaine intermediate is nothing but it is the addition product of phosphonium elite and ketone. Here, this negative and positive and negative charges are very near to each other. The attack leads to the formation of new carbon-carbon bond between the electronegative carbon atom of elide and electron deficient carbon of the carbonyl compound. In step second, what happened? The betaine intermediate first undergoes decomposition by intramolecular attack of the negatively charged oxygen on the positively charged phosphorus atom via a cyclic four-membered transition state known as oxaphosphatane intermediate. So this negative charge and this positive charge Negatively charged oxygen attacks on the positively charged phosphorus to form this four-membered ring. And this four-membered ring is known as oxaphosphetane intermediate. First is beaten intermediate where there are negative and positive charges are near to each other, and cyclic four-membered ring structure in which oxygen phosphorus bond is there. This is known as oxaphosphetane intermediate. And in step third, the presence of oxaphosphetane intermediate second can be detected at 80 degrees Celsius, which decomposes on raising the temperature to zero to form alkene and triphenyl phosphine oxide. So this oxaphosphetane intermediate can be detected at minus 80 degrees Celsius. And if temperature increases to near about zero, it will decompose. Triphenyl phosphine oxide is a stable compound. The formation of the phosphorus oxygen bond is a part of the driving force. As this phosphorus oxygen bond is stable one. So it is the driving force of this reaction is formation of strong phosphorus oxygen bond. Large amount of energy is evolved through the formation of very strong PO bond near about 535 kilojoule per mole. Wittig reaction is an important method for the synthesis of olefins, that is alkenes, from carbonyl compounds. These are the synthetic applications of Wittig reaction. We can synthesize alkenes. So remember, if this is a phosphorus halide, from this phosphorus, whatever part is there, this part will directly attach doubly bonded to this carbon. Here will it will attach. See, this is the part. This is the only reaction that is going to happen in the Wittig reaction. So acidophenone upon reaction with phosphorus halide gives alpha methyl styrene. Benzaldehyde reacts to give styrene. Similarly, we can synthesize ethyl cinnamate. So for the synthesis of ethyl cinnamate, we need this part doubly bonded with phosphorus. See, this is the part, this part. And it reacts with benzaldehyde to give alkene, the desired alkene. For introduction of an aldehyde group, we can prepare the specific phosphorus halide in which there is CHOCH3. So this can be attached here and we get this product. And after acidic hydrolysis, cyclohexane aldehyde. And the for bifunctional Wittig reaction, the if there are two aldehyde groups, we can create a cyclic molecule. But for this, we also need a symmetric phosphorus halide. Here also triphenyl phosphate group and here also triphenyl phosphate group. This will react with this and this will react with this. We get the cyclic system. For the formation of carbodiimide, which is used in the formation of amide bond in peptide synthesis, it is so R and double bond C double bond O. Alkyl isocyanate react with this trialkyl P double bond O group. This attacks on the carbonyl carbon of isocyanate, and this double bond attacks on the phosphorus. We get the carbodiimide finally. Thank you.